So we're going to talk about momentum and impulse today. Momentum is inertia in motion. If you remember, inertia was Newton's first law. So an object at rest will remain at rest, and an object in motion will remain in motion at a constant velocity unless acted upon by an unbalanced force. Momentum is only talking about the part of that that is in motion. Okay, so not the at rest part, just the in motion part, which means that we need to have motion or a velocity. Okay, and it does depend on velocity and mass. Okay, so it depends on not just how fast, but in which direction. Okay, it is a vector. Okay, it does depend on direction. The symbol is the lowercase letter p. There's no real reason that's written down out there that we know of this, okay? We're not going to use the lowercase m because it's used for mass, and it's right here in our equation. The capital P we just got through using for power, so we need something different, so we're going to use this lowercase p, okay? The equation, momentum is equal to the mass of the object multiplied by the velocity of the object. The units, we don't make a new unit for this, okay? We're just going to take the mass in kilograms times the velocity in meters per second, and we're just going to use all of that together. The momentum will be measured in a kilogram multiplied by a meter per second. So another way to think about this inertia, okay, is how difficult it is to stop a moving object. Again, the object needs to be moving, okay? So in order to have inertia. So if you're trying to stop something that's moving, you can think about it in a couple of ways. If I'm trying to stop a really, really big object, okay, it's going to be difficult. It has a lot of momentum. If I'm trying to stop a smaller object like a bike, okay, if it's not moving very fast, it's pretty easy to stop. Okay, but if someone's racing by me really fast and I want to try to stop them, that's going to be very difficult. It's going to have more momentum. Another thing to remember is that momentum isn't just based on how fast you're going, okay? It's based on mass. So say I have a truck or a train coming down the tracks, okay? And that train is barely moving, okay? I'm still not going to want to be the person here trying to stop it with my bare hands, okay? Because that train is going to have a lot of momentum, okay? Why? Because it has a lot of mass. Even if the velocity is very small, okay, it's going to have a lot of momentum. It's going to be very difficult for me to stop this train, okay? Okay, so that's a little bit about momentum. The next thing we want to talk about is impulse. An impulse causes a change in momentum. So down here we've got this picture, okay? The baseball's coming in. It had a velocity coming in this way. And the next thing you know, it gets hit by the bat, it's going to have a velocity going out that way. That's a change in momentum. It's changing its velocity, so therefore the momentum is changing, and an impulse causes that change in momentum. Symbol. Again, it's not quite so easy. It's not letter I, instead it's this letter J. Okay? Why? I'm not real sure. Or we can use delta P, because remember, delta means the change in, and the lowercase p means momentum. So it literally just means change in momentum, okay? So the change in momentum is the impulse. In our class, we'll be using delta P, but other places you might see it written as a J, okay? Units are still kilograms times meters per second, because when you subtract things, the units don't change. For example, if you wanted to know how far you moved, and you started at 2 meters and you got to 10 meters, well, you moved 8 meters, okay? You use the same unit, all right, when you add or subtract things. So, it's a little bit about momentum, a little bit about impulse, and here's how they are related. We've got this impulse-momentum theorem, okay? And it says the impulse, or the change of momentum, is equal to the net amount of force, the total force on the object, multiplied by the change in time, how long that force is being applied to the object, okay? And what we can gain from this is that if we are going really fast and we come to a stop, we're going to have a change in momentum. Okay, so no matter how fast we were going, we're going to have the same change in momentum because our mass is going to stay the same. We're going to go all the way to 0 to come to a stop. Okay? what can change, if I want to try to decrease the force, what I can do is increase the amount of time it takes for that change to occur. Okay? So, if we want to decrease the force of impact, we must increase the time of impact. This is used in everyday items. For example, in the airbags in the car, okay, you're going to hit the airbag, and that is going to make it so that you come to a stop over a longer period of time, okay, as opposed to if you were to hit the steering wheel, you're going to come to an abrupt stop. If you come to an abrupt stop, then the force is going to be greater. If you have a long amount of time, the force is going to be smaller, okay? Similarly, your car might just crumple up, okay? You hit something and you're like, why did it do so much damage? I wasn't going that fast, okay? It's built so that it will crumple. Why? Because if it came to an abrupt stop, the force acting on the car would be greater. The force acting on you would be greater, okay? If it takes longer time, which in a crumple zone it would, okay, then the force acting on you is going to be less, okay? So it's a safety measure, okay? Sometimes when you see gymnasts and things, and there's the floor, there's a spring in the floor. Why? So that when you hit the floor, there weren't springs, you'd come to an abrupt stop, okay? Short time, big force. If you hit the springs, it sinks down, takes a little longer to do that, time increases, force decreases, okay? These are a lot of safety items that have to do with impulse.